So remember that an atom is the smallest elemental unit. In other words, you take any element such as gold, and you cut it. The smallest that you can get is an atom. That's a nucleus with a proton and a neutron in the middle, electrons orbiting on the outside. However, you can make compounds of atoms, combinations of atoms. Stick a handful of atoms together, you get yourself what's called a molecule. Now, a molecule is the smallest particle of a substance that still retains the chemical properties of that substance. For example, you take water, a glass of water, and you get rid of half that water, get rid of another half of that water, another half, and keep going down until you get just one molecule of water. You can divide that molecule again because it's made of individual atoms. But if you do that, then you just have individual atoms and it's not water anymore. It completely changes. So the molecule, H2O, is the smallest you can get without changing the chemical properties of that substance. Let's talk about a couple of these types of some simple examples of molecules or atomic compounds. Here in the first figure is a monatomic molecule. Mono meaning one and atomic meaning atom. One atom. So a monatomic molecule is really just an atom. Now the typical examples you'll see of these are the noble gases. These would be, if you look at a periodic table, these would be the elements in the right-hand column. The reason why these can remain just as a single atom is that their outermost electron shell has as many electrons as possible. For example, here we have helium. The most number of electrons you can have around in the outermost shell of helium is 2. Now, if this were any of the other noble gases, then you would actually have 8 electrons around it. Again, helium can only have 2, but all of the other noble gases will have 8 electrons around it. Therefore, the outermost electron shell is full. There's no need to lose electrons or gain electrons, so it can exist alone. Here in example B, we have 2 examples. We have oxygen gas and hydrogen gas. Oxygen gas is just 2 oxygen atoms stuck together, and so we would write this as O2 because there are 2 oxygen atoms. The hydrogen gas is the same idea. You have 2 hydrogen atoms stuck together, so it would be H2. These are examples of diatomic molecules, or molecules that have 2 of the same elemental atoms. Third example would be a triatomic molecule. In other words, three atoms of the same element. This example here, we have ozone, which is nothing more than 3 oxygen atoms combined. Now, the cool thing about molecules is that's a little bit like Legos. You can build a structure with a certain number of Legos. You can take the Legos apart and rearrange them and create something totally new. We can do the exact same thing with molecules. You can take certain chemical bonds, and you can take old molecules, take them apart and rearrange them to form new molecules. Here's a great example. You have water and carbon dioxide. So water and carbon dioxide, and they just exist by themselves. But if you introduce them to a plant and also introduce them to sunlight, then you produce whatever is needed for a plant to grow. This would be sugars. So probably the simplest would be that form. And then as a result, you're left with oxygen. Now, if you count the number, we have to balance this. In order to make this work, we're going to need 6 carbon dioxide molecules and 6 water molecules in order to make this work. But if you were to count the number of carbons on the left side and the carbons on the right side, the hydrogens on the left and the hydrogens on the right, it's the same. All we did was take molecules, break them apart, and rearrange them to create something new. This process, by the way, is the process that we call photosynthesis. In the second part of the figure, part B down here, this is the opposite, where you take the plant material, the sugars, combine it with oxygen, then you reproduce water and carbon dioxide. This is the opposite. This is combustion. Combustion is the opposite of photosynthesis. Now, in talking about conservation of energy, here we address chemical energy. Chemical energy is just the internal bonding between individual atoms. So you have carbon dioxide. The chemical energy is what holds the 2 oxygens to the carbon. And what I wrote up here for you in this photosynthesis example, this is a chemical equation or a symbolic summary of a chemical reaction. Now, the chemical properties of an individual atom are determined by the outermost electrons. Let's take an example of a sodium atom. A sodium atom has 11 protons, and so in order to be neutral, there need to be 11 electrons. So in the first 1s shell, you get 2 electrons. In the second shell, you have an s and a p, so that'll be a 2 and a 6, or 8 electrons. 2 and 8 are 10. We need 1 more electron, so you have 1 single electron in the third shell. Now, here we follow the octet rule, which states that atoms try their hardest to only have 8 electrons in the outermost shell. And they can do this by either gaining electrons, losing electrons, or sharing electrons. So in this example of sodium, the easiest way for sodium to attain this octet rule is for this 1 electron to be lost. So the electron moves away. As a result, you still have sodium with 11 protons, but now you only have 10 electrons. So it's still sodium, nothing's changed there, but since there are more protons than there are electrons, our sodium becomes positively charged. Let me indicate that with this little plus sign right by the sodium. But having followed the octet rule, there are only 8 electrons in the outermost shell. It is very satisfied in this configuration. But being positively charged, it can now react with anything that might be negatively charged, create bonds. Now, contrast that with this example of neon. Neon is element 10, 1 less than sodium, where it only has 10 protons in the nucleus and 10 electrons in its shells. Therefore, it is stable. Now, there are 3 basic types of chemical bonds that we deal with. The first type are ionic. Ionic bonds deal with the electric force between 2 charged atoms. The second we're going to talk about are covalent bonds, where two atoms work on attaining this octet rule by sharing electrons. This is typically done with nonmetallic elements. In other words, the elements on the right-hand side of the periodic table. And then we also have metallic bonds, which is where you have a number of metallic atoms together, and the atoms or the electrons just jump atom to atom. The electrons just move freely throughout the metal. Then when it comes to naming atoms, this gets a little more complicated because you have millions of different combinations from over 90 elements that can combine. So it gets pretty complicated trying to name these. We've used common names, just typical words in our vocabulary. For instance, baking soda. Baking soda is just a fancy term for a molecular compound. And then anything that uses baking soda would have that soda term. For example, soda pop or soda water or just soda. Any sodas, beverages, soft drinks, used to in the past use reaction using baking soda to carbonate it. And so it was called soda pop because of the baking soda that was used. Today we have different methods, but it's still the same idea, and so we still retain that name. Problem with common names is that it's difficult to actually know what those compounds are made of. So we have a more modern approach, which uses a systematic set of rules. It will include the number of atoms, the individual atoms, and different terms within the naming sequence, which help us understand what those compounds are actually made of. Now, these rules are different for ionic and covalent bonds, and so we can't address them yet. We'll address them when we talk about the individual bonds. But there is one common rule between the two types of compounds, and that is if the compound only contains two elements, then you include this ide, IDE at the end. For instance, water. Water would be the common name. But using the modern approach, it would be dihydrogen, in other words, two hydrogens, mon-ox, mon meaning one, ox meaning oxygen, ide. Dihydrogen monoxide. That would be the modern name for water. So in the next videos, we'll talk about ionic bonds and we'll talk about covalent bonds as well as the naming sequence for each type.